In this video, I'm going to talk about some issues I found with the 3DMakerPro Eagle scanner and rolling shutter artifacts that there are in the imagery that it captures. What is the Eagle scanner? The Eagle scanner is a SLAM-based imaging device for capturing an environment. It captures the geometry of the environment using LiDAR, which is a directed light beam that scans around the scene to tell how far away things are from it. And it has an IMU, an inertial measurement unit, to measure how the device is tilted and accelerating and things like that. And it has 4 wide-angle cameras. This is the max version that take pictures. So you carry this device around and it takes LiDAR measurements and it takes photos and then combines those through software to produce point clouds like the blue in the lower left, colored point clouds by combining the point cloud with the images, and then can also be used to create Gaussian Splats to give realistic looking views of an environment, a sort of 3D model that you can fly through or walk through. This is an example of a Gaussian Splat model. It's a model made up of little mathematical blobs in space that have color that are sort of fit to a variety of photos to position them and scale them and color them. And once you do that, you can view those in software and sort of fly through or walk through a scene. The little photo pieces in the middle are where the actual scanner was and took pictures, at least one picture sampled from every second for those. So the process of making a Gaussian splat is you need a lot of photos taken from different vantage points, and then you need to align those and know exactly what the sort of optics was for each camera that was used to take the pictures, and then software can like align all those together and then go through a process of training a Gaussian splat model. And then once you have that model, you can visualize it. Now it's imperative that you model all the lenses correctly with the optics, and that you know exactly where every camera was positioned. And if you do that and you have in your scene things like the mural painted wall and lots of details, software can do a very good job at learning a model and allowing you to create something like this that represents that 3D environment, and you can visualize it from any angle that you would like to. Gaussian splat models have artifacts, and more artifacts if you view the scene from far from the original positions where photos were taken. There's often floaters, sort of these little blobs in space that occur as well. 3DMakerPro provides software for creating point clouds and colored point clouds and Gaussian splats from their device. They use both the LiDAR and the imagery to do that. Unfortunately, to date, the Gaussian splats in particular have not lived up to the quality that one could hope for. Due to that, I looked into the data and did offline processing using just the imagery through a complex approach, and that processing revealed the rolling shutter artifact that I will talk about in some detail in a few minutes. I'd like to express my thanks to Tin Nguyen for giving me the data to work with, and acknowledge the use of RayStudio to extract the images from the scan, and the use of EXIF tool to label images with which camera the images were captured from. Also, Agisoft Metashape, which is a great tool for working with photogrammetry data and preparing data for Gaussian splatting. Here I used it to align the images and to show what the camera models are and things like that for the images. It's also nice because you can do rolling shutter correction. Finally, a big thank you to the folks that developed Lickfield Studio. That is a software for training Gaussian splats and so much more. Once you've aligned all your images and sort of prepared them all in a Colmap format, you can train them to create the Gaussian splat and then visualize it. So I made extensive use of that tool. It's a great tool you can download, and if you'd like, you can contribute to the further development of that software. So what is a rolling shutter artifact? Sorry for waiting several minutes into the video before getting into this. Less expensive cameras typically have a rolling shutter, which means that if you think of the whole detector array, it reads out one line of that at a time. And so the time that's integrating the light falling on the sensor is at different points in time from the top of the sensor to the bottom of the sensor. So if an object is moving, or the camera is moving relative to the object, the image of that object will appear distorted. So this graphic from Wikipedia shows a fan blade, and if it's rotating and you're imaging it, the top of the fan blade is kind of on the right side in the image is at a position, and the fan blade is moving, and so the blades are changing position as we go from the top to the bottom of that, and so they actually are at different positions in that image as we get to each time that each successive line is read out. On the bottom of that, it shows a car moving, and so the car is moving forward, and so as we scan the image, say from the top to the bottom here, the top of the car is at one place, but it's moving forward, and so as we read down, the detector further lines down towards the wheels and towards the ground itself, the car has actually moved forward, and so it appears distorted. Those can be pretty subtle effects and not be noticed in individual images, but when you start matching up and aligning all these images together, this effect can really be detrimental to your ability to take multiple images and fuse them together into a 3D model, either a meshed model or a Gaussian splat or anything, because the objects aren't at the positions relative to the detector pixels that they should be, so you need to compensate for that. So with the stage set, let's answer the question, why did I embark on this and go through all the trouble to process data outside of RayStudio to create Gaussian splats? Let's take a look at some example output from RayStudio to show what I mean. This is example one produced by RayStudio, so just example one's a portion of the scene viewed in this frame. The RayStudio processing combines both the LiDAR and the imagery together, and it looks sort of somewhat okay here. The car in the foreground on the left is a little bit jumbled. It doesn't appear really clearly. The building to the left side appears fairly good, about, from the ground to about 2/3 of the way up, and at the top it becomes really unsharp. The right edge of the building almost seems to be a little bit not straight. The utility pole on the right looks sort of okay, but it gets to the top and it becomes kind of not that clear. But I'll call your attention to the topmost piece that's sticking out vertically to the left, and that is nice and straight. So again, this is a combination of LiDAR and the imagery. Later in the offline processing versions, I only use the imagery. So if there's things that appear only to a certain distance here, that may be partially due to the limitation that the LiDAR from the scanner goes out maybe 70 feet or 70 meters. I'm not sure. So let's take a look next at processing with the offline processing using just the imaging without rolling shutter correction. So here's example one, processed with the offline processing but without rolling shutter compensation. You can see that the scene has like more contrast overall, and the elements of it have a lot sharper appearance, particularly down closer to the ground. The top of the white building with the blue awning on it is sharp on the top. The windows on the brown building on the right are nice and clear. The car on the left side in the foreground appears much clearer than it does in the RayStudio output. But as we go up in the scene, you get to maybe 1/3 of the way up the building, and it starts to get very blurry. And so there's something going on there. The big building appears in the background. So since we're not using LiDAR, we're just using the imagery. We're not limiting ourselves to a certain distance away. And that's why we're seeing this building appear. And it is not too bad, kind of sharp lower but as we go up, it gets really, really blurry. And on the telephone pole, it's the topmost horizontal piece. Here it's like bent. I think I said it was vertical when I'm talking about the RayStudio output, but it's horizontal, and it goes out from the pole and bends down. So there are elements of this that are nice, but also as we go up further vertically off the ground, things deteriorate quickly in image quality. Here we're looking at example 1 using the offline processing, but using an approach that employs rolling shutter compensation. We can see the result is just clearly far superior. Everything on the ground is as sharp as it was before, but as you go up further off the ground, everything is much, much sharper. You can see the building on the left all the way to the top is nice and crisp. You can see in the background, the tall building behind is nice and crisp, and you can make out some structures even on its very top. And when we look at the telephone pole, that horizontal beam coming off near the top of it is nice and straight and clear as well. So this is quite a good result and much better than it appeared in either the RayStudio output or in the approach using offline processing without rolling shutter compensation. Example 2 here from RayStudio shows not too bad of a result. The slats look, sort of okay, but a little bit jumbled. The silver vents or whatever they are at the top of the building look, pretty much okay. And we can actually see the building in the distance, which we didn't see the building in example 1 in the distance, but here we see it. Anyway, if you just take a look around the scene, we can compare it to the output without rolling shutter compensation done offline next. Looking at the offline processing here without rolling shutter compensation, the results are probably worse than they are with RayStudio. The slats look good in some places. Maybe the traffic cone looks okay, and some of the text is more readable. But the horizontal lines of the siding are messed up. The building in the background, you can't see any of the windows on it. And above the roof line, you can see some artifacts. It's not clear if those are really a result of the processing here specifically, or if the vantage point here was raised a little bit, and so we're looking at part of the scene that we were not looking at sort of above the roof line. But anyway, the RayStudio processing probably looks better for this example. This result, computed offline with the rolling shutter correction, is by far the best. The building in the background, the windows are all, or floor level markings are clearly visible. The siding has nice horizontal lines. The slats are much more clearly designed, that being the vertical purple slats. The signs are nearly readable, some of them. The cone looks good. Everything looks just much crisper. The only potential downside here is above the roof line, where we see these colors and stuff. That's usually something that you see looking at an image or some reconstructed region that the camera never saw. It could be that the LiDAR helps that in RayStudio, or it could just be that the vantage point is a little higher here, and so we're trying to render something that we never saw. Anyway, again, this result is the best of the three. Example 3 here from RayStudio doesn't look very good overall. The mural itself is extended up on top with more red beyond the top of the building. The ground does look pretty good, though. I imagine the ground here looks this good because it is combined with the LiDAR point cloud, because experience here has shown me that the ground doesn't appear good near the camera track from just the imagery alone. The tall building that we looked at in example 1 doesn't look very clear, and the elements on the ground, the cars kind of look okay. The vegetation at the bottom of the mural is not very clear, nor is a post that's at the bottom of the right edge of the mural with a chain on it. So let's just keep those in mind as we look at the results from offline processing. In this offline processing result, we see that the mural looks much better. We can make out vegetation and the post with the chain at the bottom of the wall much better, and clearly see the building in the distance appears quite a bit sharper. The vehicles look good, but closer on the right side, we don't see really the vehicles. And I will call out that the ground for the processing results here are really not very good for the offline processing. Probably the LiDAR helps a lot there in the point cloud that's combined with it. It could also be that training in Liquid Studio with better parameters would give a better result, even just from the imagery. But that's remains to be seen. Anyway, so this is the result with out-rolling shutter compensation. Example 3 is shown here with the offline processing with rolling shutter compensation, and we can see that the result is the best one other than for the ground. The mural is nice and sharp. We can see the plants and the post with the chain. We can even actually make out a bunch of the chain coming forward to us from that post on the lower right corner of the mural. We can almost read the sign about towing. The building in the background, the tall white one, looks nice and sharp, and we can see the right side of the image closer than the cars has more details as well than we were able to see in the processing without the rolling shutter compensation. So again, the ground could be a lot better, but other than that, this is the best processing result. Okay, let's review. So RayStudio fuses the LiDAR and the imagery together. It does produce the best looking ground, and the overall output, though, looks fairly poor quality, and it can limit the visibility of distance buildings. Despite these limitations, some kind of fusion approach probably is the best. In the offline processing, we just use the imagery. The processing approach that I applied aligns the fisheye images, and that's important because we need to align the fisheye images because they're actually in the format of the image on the detector. And because rolling shutter is an issue where there is motion of the camera that is significant relative to the readout of each line of the image in a rolling shutter camera, which the Eagle has rolling shutter cameras. So we need to apply the processing on the fisheye images themselves when we do the alignment and do rolling shutter compensation. When we do that, the imagery looks really good. But because it is an image-only approach, the ground looks bad, and we really should be using some kind of a fusion approach. So ideally, we would do some kind of optimization, which aligns the imagery. When it aligns the images together, it also aligns it to the LiDAR and does some kind of a fusion approach. That way, when we're processing the imagery to train the model, we can also have access to the ground point cloud, colored point cloud. And if we process that together, we would probably do the best job. Okay, let's have a go at describing this issue with different lens models and rolling shutter or no rolling shutter. Actually, I'm going to put off the different lens types of equidistant and equisolid off until later, and we'll just look at the case of equidistant with and without rolling shutter compensation. So I used RayStudio on your Hawaii street data set to extract frames, basically the first step of the process. And then what I did was I extracted from each of the 4 cameras that were used 1 frame per second data, and there were a total then of 930 frames, nearly 232 from each, one extra from the front camera. Anyway, I then went in and manually segmented. Now, it's not a perfect segmentation, but it's really pretty good. If we go through here and click through the list, we're here in the equidistant no rolling shutter compensation version, but we're looking at the left camera, and if I click through here just to give you an idea of the masking, I didn't mask the shadows of the people, just the person, just you itself, and you can see this took hours to do. I don't know, maybe 6 or 8 hours to go through all of these images. I went through every one though. If we look at something from another perspective, let's look at the back camera, for example. You can see you're over here on the right, and if we click through these, you can see what that masking is like. Of course, the front camera, you're in that less. So if we look at those images, there's not too much to the masks. But your feet are in there occasionally, and I mask those out. So quite a lot of work to do that masking. I had also run the EXIF tool to label the images. So if we look here under the camera calibration, we'll see eagle front, eagle back, eagle left, and eagle right with the right number of images in each. As I say, this was the equidistant fisheye with no rolling shutter compensation. Now, we can look then at what the we can't see the initial, okay, and the adjusted here. So these are the camera parameters for each. So the focal lengths came out within just a couple, right? That's a good sign that things are working right. We had these set to 0, and that's important as well, I think, for using this stuff later if you want to do Gaussian splatting or something. If we look here at the distortion plots, we can see here what this looks like. It looks overall pretty good. There's a bunch of stuff shooting off the edges. Let's see, RMS 288. And we can go and look at the radial distortion plot, the decentering. So I should study those things probably in more detail. We can look for another lens here, right click, distortion plot, okay, and see again what we get. Anyway, we can go through and look at all those, and we should probably do that in more detail. I then did an alignment, and it took several tries of looking at the results and pulling out certain cameras and going and putting other certain cameras in and all that. But in the end, after doing that process very carefully, and this is what we come up with. And again, this is the no rolling shutter correction. One thing that's, I think, important to do, in addition to that masking is critically important, is to then look at the cameras. So if I look at like back here and I click on this, we'll see this highlights in pink. And if we go through this list, just by on the left side here going down, we see that the pink positions, because I know that you were walking in a line, and these are 1 second interval shots. They should be pretty much all in a row, like in a line together, one after the other. If you do this and see a pink appear somewhere else, like forwards a ways or wherever it, and then comes back, then it's probably an error. So as I say, I went through this several times, looking for errors, pulling those cameras out, re-optimizing, and then trying to align that camera again. So I think that this is about as good of an alignment as you can possibly get, given the masking was done. I did run this with estimated as opposed to sequential, because I'm not sure how sequential handles the 4 cameras. Here we're down to look at the other one, the left, and so it's highlighting all of them. But if we go in there, we can look at the left camera. Now, it may be hard to see these, because if they're plotted completely in profile, then you won't see it there. So you might have to rotate the view around to see it. Anyway, so I believe that these are all very good in their placement. If we go over here to the exact same version of this, but run with the rolling shutter correction applied, we can look there, and we have exactly the same images. So they were masked exactly the same way, using exactly the same masks that were used for the rolling shutter version. Now, if we look here at in this one, we can go through in exactly the same way. So like for the back camera here, and again, I went through this multiple times, pulling out things that were not well aligned and then optimizing and realigning and all. So I think that these camera positions and alignment is very, very good and sound as well. Now let's take a look at the sparse point cloud for each. So let's first look at the no rolling shutter version. Okay, so these are the cameras. Now if we turn on the sparse point cloud here, we can see what that looks like from the top, and generally looks pretty good, right? There's the street that you walked on, there's this chain you walked over here and walked around. Looks generally pretty good. We can look, though, well, let's take a look then at the other version. So the rolling shutter corrected version for the top view. Hopefully it's set to that here. It is. So if you look here and compare these two, this one looks better. Like these lines of other things, particularly like down here, this looks a lot better in this rolling shutter corrected version than if we go to the no rolling shutter. It's blurred out. This isn't as clear. Like nothing is quite as clear if we don't use rolling shutter compensation. It's more informative if we look at a different view. So because the taller we are up from the center, like the top of the camera or whatever, the rolling shutter effect is going to have a worsening effect on the ability to match points and do it in a consistent way across the image. So if we switch here instead to a front view, we can see here, so the street's coming towards us, this dead-end street that you looped around. Here's a tall building in the background that's just off the street. There are other buildings further away in the background as well. But if we look at this same kind of a view of the rolling shutter corrected version, which we can go to back here, look how nice and crisp these lines are up and down on this building. This is all very sharp. If we go out here, these other buildings in the background appear much more well represented in this rolling shutter corrected version. So I'll go back to the no rolling shutter again. We can see how it's not very clear, these buildings in the background. Go back to the rolling shutter corrected version and how much better these buildings appear. Again, if we zoom back in here, look at the lines of the vertical facade of this building, and this is the rolling shutter corrected version. And if we go back to the no rolling shutter corrected version and zoom in there, it's just kind of a mess. So I think rolling shutter correction is still very important with the scanner. This scan was from, I don't know, within the last couple of weeks. So whatever firmware is implemented now still has a rolling shutter issue for the Eagle. And I think that that's important to note. So we could take these forward, and I'll do that in a bit to do some Gaussian splatting from them both, and we can take a look at the results. But I think that this analysis alone is very kind of clear on what we have for a better solution with rolling shutter correction. I'll go back here and just put this on the screen so we can see it for what the cameras look like. I need to screenshot them myself or something to compare them, but let's look here. So this is the no rolling shutter correction, Eagle front. Let's look at the distortion plot. It would be nice to keep these on the screen, but we can't while we look at another one. So this is the front camera. This is the back camera. This is the left camera. So I'm doing this so we could freeze frame these in the video and then compare them or something, extract them and compare them. And then the right camera distortion plot. So these are on like 283 maybe or something for the RMS. All right, let's go back to the one when we did rolling shutter correction. and look at the camera calibration that it figured out, and look at the distortion plot. This is like 270 something now. This looks cleaner. There's less pixel, less distortion areas jumping far off the image. Distortion plot again looks nice. 214. I think that's probably lower than the other. If we freeze frame these and pull them out, we could compare them. 291, this one's jumping off more. This is the left camera. Maybe there's some opportunity to do slightly better with the alignment, distortion plot here. This one's not quite as good, and is the right camera. So I don't know how much of that's affected by the rolling shutter correction and all, but it would be interesting to delve deeper into this. You can also look at the profiles for these, and that might be interesting to do as well, or look at the camera calibration values we have, and look at some math and things like that. Anyway, that's all for now, but I think definitely rolling shutter correction is still something that is very important to apply if you want to get good results, and that needs to be done as the very basically first step in alignment, because doing the alignment with rolling shutter correction is the way to correct that. If you first take the images and go to a pinhole projection, undistorting them, and then try to do the matching, you can no longer apply the rolling shutter correction because you've undistorted the images, and they don't make sense in terms of the focal plane and motions, and you can't apply that uncorrection anymore. Okay, kind of long, but that's it for now. So in closing, I'll just say that the process I followed here is not one that you really want to follow. It's not a push-button solution. It takes hours to segment out the camera operator, etc., and then a lot of work to run camera alignments and look at them and evaluate and pull cameras out and re-optimize. So it's not a push-button solution. I'm not proposing it as such. Also, I really do believe that fusing the imagery and things with the LiDAR is really the way to go, and really in an indoor situation where you don't have good features like painted walls and things like that, no textures, LiDAR becomes even more important in the process of doing the modeling. So we definitely want to do it together, and the right place to do that is really within RayStudio, but I think that the software needs to improve quite a bit, and that is possible because the results here show that the cameras can take reasonable imagery, at least outdoors, and we can get good results. Next, I'll just mention that it's kind of unfair that the results that I show from the offline processing have in it a person who's evaluating and making decisions. But it's also crippled because there is no use of LiDAR and the IMU and all that. So that really should, if pulled into the processing, be superior to just the evaluations by a human in the loop. That's all. Thanks so much for watching and sticking through to the end.